So we're going to be talking about the physical property. Don't forget where we started in the morning. We have the so many things we take. So now, going back to our question, you have heat capacity, which is C, is the amount of heat required to raise the temperature of a body by 1 unit by 1 unit under specific condition. What that means is that what I'm saying in essence is that heat capacity is the amount of heat required, which is Q, to raise the temperature of a body by 1 unit under specific condition. Now, if you look at the unit of heat capacity, now don't forget I said earlier that Q equals MC change in temperature, right? This is what I said earlier. This is change in temperature. Now, if I want to bring my CL, let me just start afresh. I said this earlier. Now, if I want to bring this out, heat capacity C will be equals to Q all over M delta T. Bringing this out. If I want to bring this out, all I need to do is just divide by M and by dt. If I divide by M and dt, that will cancel this out, and this will stay here as a denominator. Do you understand that? Do you understand that? Good. Now, don't forget that the unit of this is what? What's the unit of Q? Our Q is heat energy. What is the unit of that? Joule. What is the unit of M? Mass. And what's the unit of temperature? Kelvin. So that's how they got Joule per kilogram per Kelvin. That's how they got this.
And Kelvin and centigrade is the same measure?
Now, a change in temperature is normally put as K, Kelvin. It's the same as temperature.
Centigrade.
Yeah, it's the same as centigrade, but there's a conversion factor for that. But in most calculations, you use K. You use your temperature to be in Kelvin. So that's the general case that you use. Your K is going to be your temperature is going to be in Kelvin, and the conversion factor is that your temperature in Kelvin is equal to 273 degrees Celsius plus your temperature. It's equal to 273 plus your temperature in degrees Celsius. This is the conversion factor. Your temperature in Kelvin equals 273 plus your temperature in Celsius. What I'm saying in essence is that this is a conversion. This line you see here is a conversion factor. What I'm saying is that if I give you 0 degrees Celsius, 0 degrees Celsius equals to, if you put 0 degrees Celsius and add it to 273, it's equal to 273 Kelvin. Okay? If it is 2 degrees Celsius, put 2 here and add it to here, you have 275 Kelvin. Okay? If it is 10 degrees Celsius, put 10 here, what are you going to have here? You have 283 Kelvin. Now, because we are dealing with change in temperature, because what we are dealing with is what? Is a change. A change in temperature from here to here. What is that value? No. Look at it very well. 10. A change here is 10, okay? What is a change here? 10.
It's the same.
It's the same.
That's why we don't need.
That's why we don't need to convert it.
That's invariably you don't need to convert it because you're going to subtract one from other.
So you just proved the point that you don't have to convert it.
Easy.
So you understand what I'm saying? You don't need to convert it. So a change in degrees Celsius will always give us a change in Kelvin. So you don't
Only obviously the question was how many kelvins were into centigrade. You need to do a conversion and say 275.
Yes.
Yes, if the question was different,
Yes.
it went differently.
Yeah.
But in the actual physical calculations like this, you
And
can
it's
easily.
because a change in temperature. Because if you have 273 to the first one, you add it to the second one, and you take them away, they will definitely remove themselves.
Okay.
So now, this is the formula. The formula is very important, please. This formula is very important. Take note of this formula. It's very, very important. So each supply to a food material will be the mass of the material multiplied by specific capacity of the material times temperature difference. That's the formula you need to know. Unfortunately, open book. You are bringing it in. So it's easy. Now you want to know what you're supposed to use per time. That is the only essence of all this. So that's that. Now, sensible heat changes. This is very important. Sensible heat changes is this. Now, if you are heating your water, if you heat your water, you are boiling water, the temperature will begin to rise. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. When you get to 100, you are eating the stuff, and it stay in 100 for a long period of time. Why? Why is it doing that? I will tell you what it's doing. Now, at that point, water is changing phase from water to steam.
Yeah.
So for you to break the molecules bringing the water together, the forces bringing the water together to turning it to steam, you need to supply energy. The energy you are supplying at that point in time, they call it latent heat. It's hidden. You cannot see it. You cannot see the effect, but you are supplying it. So energy that does not energy that you supply that does not induce a change in temperature is called latent. It's not. If you look at your dictionary, latent means hidden. Something you're not seeing. But the sensible one, the one that occurs between 0 and 100, sensible. You can see a change in temperature, sensible heat. But for example, let's start from the scratch. Ice.
From frozen.
Ice. Thank you. From -10 or wherever. When you get to ice at 0.
Yeah. And you still got ice, and then you got water.
Water,
it doesn't change temperature until all the ice is
Thank you very much. Thank you very much. Thank you very much. That's the latent heat changes. These are not accompanied by a change in temperature. And sensible heat changes, they are accompanied by a change in temperature. Let's see this graph. You can see you have the ice. You are supplying the heat. It's going sensible. At this point in time, at 0 degrees Celsius, you have latent. Now, when it finished, you start having it going up to 100 degrees Celsius. Then to turn to steam, it is stationary again. So this is just that. Just can see during melting, it's going to stay at 0. During boiling, it's going to stay at 100. At normal atmospheric condition, degrees Celsius. Now, how much energy is required to carry out that task, assuming that there are no heat losses in the system? Specific heat capacity of water is 4190 joule per kilogram per Kelvin. Now, you know the formula. That the formula to do this is what? Can we cross the formula? Q equals what?
MC times change temperature.
The F here is given to us as what?
1,000 kilograms.
And the C there is given to us as what?
4190.
4190 joule
Joule kilogram
per kilogram per Kelvin. Times change in temperature. What is change in temperature? Huh?
57 degrees.
57? No, it's not going to decay.
Kelvin.
It's going to decay because this formula they can cancel out.
Yeah.
It doesn't really matter. You have proved that to you that whether it's in degrees Celsius or in Kelvin, it doesn't really matter. So you can see that will cancel out each other. Then you're going to have. Now, like I said, the first thing you want to ask yourself is that what are you giving? You are giving mass of water. You are giving the specific capacity of water. You are giving the temperature difference, which is 57 K. Energy supply is what you are asked to find. Then, and you've told me how to do that here. So you have your water coming in, mass of water, specific capacity 57 K. This is what we have here. Then by the time you punch that into your calculator, you have this. Then I have this in joules, and I can convert it to kilojoules. Okay, you can convert it to joules or kilojoules because sometimes it's going to be containing large numbers of zeros. So you can even convert this to megajoules. You know, mega is 10 per 6, kilo is 10 per 3. Now the answer that I have there is 238,830,00 joules. This can be written as 238,830 kilojoule. That's one. It can be 283 megajoule. Mega is power of 6. So in the exam, you may see this as your final answer. So you just have to be familiar. You need to understand that you can express all these things in various ways. Now the next thing, sorry, do you have any question here?
No.
Is it clear? Straightforward?
The only thing I'm struggling with
Okay.
is you've got 57 kelvins.
Yep.
So for the 57,
Yep.
we took that from, where did we take that?
72 minus 15.
Change.
Gotcha.
Temperature.
Huh?
That should change, right?
Yeah, change
gotcha.
temperature.
So
Yeah,
you just subtract those.
subtract them. Yes.
Right. I
You
should-
know that your 72 degrees Celsius is the same thing as 72 plus 273 Kelvin.
Yeah.
You know that your 15 degrees Celsius is 15 plus 273 Kelvin. But because you're going to subtract them, this will cancel out. So that's why you don't need the conversion.
I've got a question.
Yeah.
Your kilojoules and megajoules, yes?
Yep.
Because you put in comma or whatever.
No, this is not common. This is dot.
So I don't know in English. How did you differentiate? Normally you put commas or anything
No,
like that.
if it is
Decimals.
comma,
Then we don't put anything there.
if it is comma,
Yeah.
it's different. Now, comma is like counting from 3. It's like
No, no, I
Like
understand.
2.9, she's thinking like 2.9.
Yes,
then you
yes.
go 2.9. Now looks like 238.830.
Yeah.
So normally, I don't know, the way we were taught, we don't put any comma. If you were to differentiate by comma or whatever, you don't then put any commas in the actual big number.
But here should be comma
Yeah.
because it's
Very big one. If this one is assuming this one is 223.883, then you have your comma here.
Oh, okay, so you do this one. Okay.
This is dot.
Yeah, no, I understand it.
This is decimal.
if we're not going to show commas, it's going to be
It
the
doesn't
same.
matter.
Okay.
The reason for comma is for you to avoid, is for you to do the counting very well. No, comma is not important. It's not important.
No, that's what I mean. Normally we don't put comma.
It's not important. Yeah.
Number.
It's
If you
fine.
put-
It's fine. You're right. You're right. You're right. But sometimes people put commas so that they can know how many of them. You know, they are in 3, a group of 3. So it's very easy for you to count them to know. This is not the answer, please.
Mhm.
So is that clear?
Yeah.
Let's go to the second question.
So that's my last one. If the temperature goes from, say, 75 down to -10,
Yeah.
is it the same? Or do you do it,
If it is 75 to
or do you put the temperature change in as a minus?
now, let's take it from one after the other. The question says if the temperature goes from 75 to -10, the question will now say what is the amount of heat you've removed,
Yeah.
which is going to be the same thing. But now you have two different phases. If it is water, it's going to change from liquid to solid.
You're going to go to latent.
Thank you, sir.
Yeah.
Then when you
Yeah,
go to latent, you also go back to the ice.
Yeah.
It's like
This is the next example.
It's not.
yeah, you because when you do, you have three. He has a very very interesting question. Let me just demonstrate that for you before we go there. Your question is very very good. Let's say because we are dealing with increase. Let's say it is from here to here, right?
Mm-hmm.
So this will start from -10 ice to 0 degrees ice. Then it will now stay at 0 degree where this is ice, okay? Ice to ice.
Yeah.
Mm-hmm.
It will now move from ice to water
At 0 degree.
at 0 degree. That's the second phase.
Yeah.
Then the third phase will now change from water to water. Water here at 0 degree to water at 75 degree. So you have
Yeah.
3 different things to calculate.
Mm-hmm.
Here, it is going to be mass of the ice, which is going to be the same thing. It's the same thing mass of if you measure ice.
Mm-hmm.
If that ice to turn to water, it's going to be the same mass. If that water turns to steam, it's going to be the same mass. Although you can't see it, it's going to be the same mass. Now, mass of water that you have here times specific. Now, this C will now be specific heat capacity of ice.
Mm-hmm.
Okay? This C will now be the specific capacity of ice. We have that. Then change in temperature. The change in temperature here will now be what? 10. Because 0 minus -10 is 10. It's 0 first. minus 10 is 10. So here is mass of ice, latent heat of vaporization of fusion plus mass of the mass involved, specific capacity of water. Now you're going to be using specific capacity of water. Then times temperature difference, which is 75. So this will be the total energy involved. So this is quite similar to that. Do you understand that?
So you just add them together?
Yeah, you just add them together.
You've got two different...
Yeah, you can do them separately, then add them together, your final answer. So this is the same thing as this. Now if you look at the question here, the question says 100 kilogram of ice at 0 degrees Celsius. This question is simple because it doesn't go down like minus something. Because if it's minus something, it's going to start from something like this. It's going to be 3. So you have 100 kilogram of ice at 0 degrees Celsius placed in a vessel, and it is heated until to steam at 100 degrees Celsius. Now, how much energy is required to do this? Now, we've been given specific capacity of water. We've given latent of evaporation of water, or latent. Now, in some questions, you may see latent of evaporation of water or latent heat of vaporization. We've been given that to be 2256. Then, if you take note of something, can you see the unit of specific heat capacity? Can you see the unit of latent heat of vaporization? You see, these things make sense. If you look at the formula, look at this. This is Q. All of them is Q, right? This is Q, this is Q, this is Q, and you can add them together. Now, if I want to determine the unit of this man, I will just say L equals Q over L. This is kilogram. Sorry, this is joule. This is kilogram. That's why you see the joule per kilogram. That's why you can see the unit there, joule per kilogram. Or this one is in kilo. It doesn't matter. The kilo is just an indicator that is a factor of 1,000. So you can see kilo here. Because most of the time, latent heat of evaporation and latent heat of fusion, they are very huge number. So it is best, they are best expressed in kilojoule because they are very, very big. Because you need more energy to break down the ice, you will need more energy to break down water. So it's very huge amount of energy. So that's why they normally express them in kilojoules. So that's there. Now, how do we solve this? What are we giving? That's the first question. Giving. We are giving the mass of ice, 100 kilogram, temperature change in different phases, the energy supply. That is what we are asked to find. Now, the next thing you need to do is that you need to look at energy supply will be energy required for ice at 0 degree to water at 0 degree, plus energy required at water at 0 degrees to water to change it to water at 100 degrees Celsius. Then you add them together. Then you answer. That's the final answer. Let's go on. Now plus energy required. Because I didn't do that one. Plus energy required because you look at it. They said converted to steam, but the steam is to steam at 100. So you need to convert your water at 100 to your steam at 100. You look at the question very well. To convert it to steam. So you're going to include that. So when you start, now for this one, energy required for ice at 0 degrees Celsius to water at 0 degrees Celsius, that will be mass of the mass given, which is 100, multiplied by the latent heat of fusion, which is given as latent heat of crystallization of water. Okay, that will be ml. Then the next one will be mass of water, specific heat capacity. We are not using sensible heat because there's a change in temperature. Sensible heat is coming in. Don't forget that this is sensible heat, this is latent heating. And here we have heating also. It's going to be ml. But this L this time around is going to be vaporization because you are now at the water changing to steam level. Vaporization. Then here is fusion because ice is changing to water. Now put in everything. Now in the exam or anywhere, because this mass is the same. Because they are the same. You can take it out. It makes your work easier. You can factor out M. Because M is 100. But I didn't do it that way because I know people can be asking me, why did I take it and why? So what I did is just to do it one after the other. So this one is mass 100 multiplied by latent heat of fusion. Now my latent heat of fusion is 334. But now I didn't use 334, I used 334000 because I want to make sure that everything is in joule per kilogram per Kelvin. I want to make sure that I have the same unit for my energy. So I use I convert it to SI unit. Now for this, water is this. Then the specific capacity of water is 4190 joule per kilogram per Kelvin. Then change in temperature is because it's changing from 0 to 100. I have 100 for that. Then for the steam, it's from no change in temperature. Just put the mass of water and the latency of vaporization. Then the next thing what I have now, let's just see something now. Now you will discover that this is from 0 to 0. Can you observe that figure? 3. From 0 to 0. Imagine, look at the energy you supply from 0 to 0, and look at the energy you supply from 0 to 100. And look at the energy you supply from 100 to 100. Massive amount of energy to break water down to steam. Massive amount of energy to break ice down to water. But all the journey you travel from 0 degrees Celsius to 100, you are still using 45 pounds worth of fuel. All the journey you use from 0 to 0, you are from 0 to 0 using 30 pounds worth of fuel, because you are dealing with ice to water. All the journey you use to change steam to water to steam at 100 to 100, look at the massive amount of energy you use, 225 watt of fuel. I'm just using that illustration. Do you understand what I'm saying now? So you can see that fusion and vaporization, they require a huge amount of energy. Now all you need to do now is just to add them together with your calculator. Then you have your final answer today, 300, 900 kilojoule. Very simple. This is a typical exam question.
Can I ask you, sorry, joules was expressed as kilo. So you've got kilojoules and joules, because you obviously.
Now if you look at this, I've converted my, this was meant to be 2256 kilojoule per kilogram. I've changed it to 2256.
Yeah, that's fine, because later on then you obviously, I guess,
Change it back.
Yeah, I changed it back to kilojoule.
Yeah, you change it to joules, so obviously you've got kilos, what was it, kilo, you time 100 kilos by 334,
Yep.
334,000 joules per kilo, so you've got 2 kilos in joules.
This kilo is down.
Yes.
I like that observation. You know, sorry, I like that observation. It's just to show that you are following. You understand? You can say, okay, why should we kilo square? But immediately you recognize it's down, you know it's going to cancel out each other. It's a very good observation. So this is down. It will cancel out this. You are left with joule. This is up, down, cancel out, down,
Up.
So, down, up, cancel out. You are left with joule. Up, down. You are left with joule. So you can add them together. Very good observation. So if you are doing the rising, you would definitely know with your units. If you are doing the rising, you definitely know with your units. That's another example. Now, can we do this activities for me to know that you understand what we've been talking about? Can we? You can do it as a group. You can do it if you want to. If you are comfortable, you can do it on your own.